you're right, I forgot. Sorry, Yakov told me and I forgot. There's some lectures by Daniel Bauman on cosmology as well. And then I also have a CQG review article, which I wrote with some collaborators 2 years ago. Okay, so this kind of, which is certainly not as good as these other two references, but there you go. Okay, so to start off with, as I said, I just want to talk a bit about some of the physics in cosmology. Okay, and just like in general relativity, we have postulates, okay, which set up your theory. We have the same in kind of the standard models of cosmology. And so this is often called the cosmological principle. And so the first, it's got formed of two parts. Okay, the first part, let me write it down and then we'll see kind of what this is all telling us. Okay, so, okay, is my writing big enough? Ish, okay. Okay, so the first assumption in the cosmological principle is that the universe is a manifold, m times r, okay, with a Lorentzian metric G. It's going to be 4 dimensions in our case, so M is going to be a 3-dimensional manifold. And we make some assumption about the existence of a special class of observer. Okay, so in particular, we'd like the lines x times r, okay, which are what's called the trajectories of something called fundamental observers. Okay, so we want these to be time-like geodesics, orthogonal to the t equals constant hypersurfaces. Okay, at each point x comma t. So this is quite a fancy way of saying that there's going to be some fundamental observers who are going to be able to see what's going on. Okay, and because they exist, we can use their time coordinate to set up the Lorentzian metric G, okay, such that it takes this split product form. Okay, so minus dt squared plus gm, okay, where this here t is often very fancily called cosmic time in cosmology, okay, and it's just the proper time of the fundamental observers. Okay, so this is, let's say, a bit of a technical assumption that's going to restrict the form of the metric, right? And so this is the first principle. What is the second principle, second assumption in this cosmological principle? It's the fact that the universe at each time, okay, it should look the same in all directions. Okay, and also, okay, so if you are a fundamental observer, okay, at any point in time, if you look around, okay, yourself, the universe should look the same, and no fundamental observer should be different, okay, and also to any fundamental observer. Okay, so mathematically, what does this mean? Right, this second principle here is telling us that the Riemann tensor of this metric GM here, which is on the spatial slice M, okay, should be invariant under rotations. That's what that is telling us. Okay, so in particular, we're saying here that we're assuming isotropy. Okay, so isotropy means the same in all directions. Okay, this is telling us that the Riemann tensor of this metric GM, okay, should be invariant under rotations. All right, so this is the first part, all right, is that no matter which way you look, okay, you should be isotropic. And then the fact that we say here that it shouldn't matter which fundamental observer you pick, right, is saying that we want the universe to be isotropic at every point in space. Okay, so we also suppose isotropy at every point in your space sections, I guess, or in M. Okay, so the point that we pick is not special. And so this, in fact, if you have a space which is isotropic at every point, that tells you that it's going to be homogeneous. Okay, and so this bit here tells us that this manifold M and the metric here should be homogeneous. So this brings me to the first diagram on here, which is just to give you an example. So just ignoring what I said there for a moment, isotropy and homogeneity, they're distinct ideas. Okay, so here, if you can see, right, we have homogeneous but not isotropic, isotropic not homogeneous, and the other way like this. Okay, but what we're assuming in the cosmological principle is that we have isotropy, okay, for any observer, and no observer should be special. All right. Now, where do these principles come from? Okay. The big thing that I guess we're really assuming here, okay, this is kind of some technical thing to get your metric in the right form. The big thing that we can verify or match with observations is isotropy. Okay, we can't check other fundamental observers, right, because we're stuck on Earth. Okay, so we can't actually go and check on the other side of the universe that they also see isotropy over there. Okay, so it's certainly an assumption to make there. But let me then talk a little bit about why isotropy. Okay. So, and again, sorry if you know this already, but I just feel maybe if you did like a math background, you probably haven't met as much cosmology and the physics. Okay, so there are two main experiments or observations, I shouldn't say experiments because you don't do it once. There's two main observations that support this principle of having isotropy. Okay, and so the first of those is what's called the emission of the cosmic microwave background. And so I just want to say a few words about this. It's important to think what is our currently best model of cosmology. Okay, we had a Big Bang. Everything is delocalized. Okay, there's just a plasma of quarks and neutrons and all these different kinds of electrons and photons. Everything is just some big, hot, very dense plasma. Okay, and the idea is that it's amazing we can even estimate it. Okay, about 380,000 years after the Big Bang, okay, this plasma cooled, okay, to such a point where atoms started to combine, okay, and these kind of certain constituent elements combined. So in particular, there's something called Compton scattering, which is this idea that if you've got free electrons roaming around, then they will interact with photons, gamma, and they'll give you another electron and a photon. Okay, but at some point, the temperature cools so much that the electrons start to be absorbed in nuclei. Okay, they start to be attracted to other protons, and they form atoms like helium. Okay, so then there are no electrons to go around, so this process doesn't happen anymore, so the photons are free to move where they like. Okay, so they're not going to be caught up by other subatomic particles in some kind of interactions. Okay, so in particular, the plasma cooled, okay, and we say that the photons is what's called, it decoupled from the plasma, okay, and they kind of traveled. Okay, so what is quite remarkable is that we now, oh, and it didn't, oh, there it's go, it did change here, okay. If you look on planet Earth, okay, if you put a detector out this way and if you put a detector out this way, we can now detect that radiation. We can detect these photons, okay, and this is what we call the cosmic microwave background, okay, so obviously it's projected down here onto 2D. And what is really quite remarkable, okay, and the picture doesn't do it justice, is that this emission, okay, of photons, so these are, it's got the spectrum of a black body object, so it means it has a certain kind of spectrum, which means that certain wavelengths should be mapped to certain temperatures and all this kind of thing. It is very nearly isotropic. Now, when you look at this picture, you're going to say to me, but look, it's blue and it's red. That's not isotropic. Okay, but that's actually because the variation here from blue to red is the order of 300 mu Kelvin, microkelvin. Okay, so it's about 1 in 10,000 parts, it is isotropic. Okay, so you see very few anisotropies. All right, so this is really quite incredible, right? If you put a detector out this way, you will measure photons, okay, which are coming at matching some black body spectrum, okay, matching to some particular temperature. So let me just write that down. Okay, so the CMB radiation, let's say, matches a black body spectrum with temperature equals to 2.725 Kelvin. Okay, and this was actually something that people used to pick up on old analog TV sets. Okay, so it's something that was actually, you know, you get this kind of residual interference coming from these photons. And what is phenomenal is that this temperature is so isotropic. Okay, if you look this way, if you look this way, it is incredibly isotropic, and there's very small anisotropies in this spectrum. Okay, and so let me just write that here. Okay, anisotropies less than 1 in 10,000. Okay, so obviously there are different models to try and explain why it is isotropic. Okay, and this is something called inflation, but that's not what I'm interested in. Okay, so this is going to be kind of the starting point for the dynamics that I'm interested in. But in cosmology, one of the, just to say verbally, okay, one of the key ideas is that while this CMB is incredibly isotropic, it still has small anisotropies. Okay, and we think that these small variations are what sources the structure that we now see in our universe. Okay, because we have to remember, just very naively, big picture, right? The universe is expanding, gravity is attractive. Okay, so you've got these two things working against each other. How on earth could any structure have formed? Okay, how do you know that they balance each other? How do you know that one is not too big? All right, so this is, I'll come back to that later. I'll talk about that later. Second thing to mention about why we can assume isotropy in the cosmological principle, okay, is what we see is large-scale structures. Okay, and so for this, we can go to the next picture, okay, which is that the universe, by which I really just mean galaxy counts, okay, is roughly homogeneous, and I think I'm going to write here, okay, on isotropic on large scales. Okay, so what I've shown you there, okay, is a picture from the Planck satellite, right, which is looking at light emitted from galaxies at ever increasing distances, okay? And what people observe is that if you look at very large scales, okay, which roughly correlates to 100 megaparsecs, means that you come onto a plot like this, okay, and you look out at whichever redshift it is. I think it's probably somewhere in the middle here, okay? And you basically take a box and you count the number of galaxies in that box, okay? And you've got a box here, 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 all this kind of thing. And then you count in that box how many galaxies there are, and they are, what we can see, isotropic because they have the same number of galaxies in that box to the level of like 1%, okay? So it is something that has some statistical significance. Okay, so we see on, yeah, okay, for a certain kind of distance. Okay, and I thought I'd just make a quick comment on what is a megaparsec, just because I found it quite funny, because, let me just write it here. Just because I think most people know parsecs, okay, from Star Wars, right? Because Han Solo says that he made the Kessel Run in less than 12 parsecs. And you've probably always been confused because parsec is not a notion of time, okay? It's a notion of distance, all right? And I think it's important to get that right. Okay, so a parsec, they basically, let's say we want to know how far this, okay, so this is the sun here in this yellow dot. We want to know how far we are from this star, okay? How can we measure it? What we do is that we take two measurements at 6-month intervals, okay, because the Earth goes around the sun. So at one point we take a measurement and we look at this star and we actually use some distant stars in the background to calibrate against. Okay, so we might see that this star appears here relative to this distant star. And then 6 months later, right, Earth is on the other side, okay? And now if we look here, it will look like the star here is appearing here relative to this distant star. Okay, and so a parsec is the distance here that would be the case if we measure a one angle, okay, change up here. Okay, so it's a measure of distance, okay, because it's the angle, it's kind of the angle, it's the distance that would have to be subtended or traveled in order to get this one angle past there. Okay, so it's a measure of distance. And maybe just to put this in comparison, okay, so the Milky Way, actually I can write it down here. Okay, the Milky Way is roughly 34 kiloparsecs across. Okay, so the scales that we are seeing, this isotropy and homogeneity, are significantly bigger than that. Okay, we're going from a kilo to a megaparsec. Okay, so it really is something that you have to see on very large scales. Okay, and I guess it's important to say that we certainly don't see isotropy on smaller scales than this, right? Like we see structure in the Milky Way, okay, and things up to that point, but at some point it starts to change. Okay, so what I was trying to set us up with all of this now, okay, is to build our way towards something called the FLRW metric, and I probably should write out their names at least once. Friedman, Lemaitre, Robertson, and Walker. I'm not going to say the history of who did what when because I don't actually remember it. But what we had, okay, on this board up here, which I can put to the top, okay, is we had this cosmological principle And really the key thing that we get from that is we get some simplification on the form of the Lorentzian metric G, okay, on account of this isotropy and homogeneity that we've assumed. Okay, so in particular, let's say here, if you have a three-dimensional Riemannian manifold, which is isotropic at every point, okay, then it actually is quite constrained. Okay, I mean, you're in 3 dimensions, right? So your metric tensor's probably got 6 different components. Okay, but when you're also assuming that it's isotropic everywhere, you're removing a lot of these degrees of freedom. All right, and so in particular, we see that it has to be what's called a maximally symmetric space, okay, a space of constant sectional curvature. And so in particular, this all implies, okay, that the space-time metric for our universe, okay, G, takes the form of an FLRW metric, okay, which looks as follows. Okay, so as before, we have minus dt squared plus gm. Okay, so gm, I guess I'm now writing as gamma, but I could have called it gm. It doesn't really matter. All right, and let me go even further. All right, it takes a very simplified form like this. Okay, so what do I have here? Okay, I have the fact that in 3 dimensions, okay, the Riemann tensor is equivalent to the Ricci tensor. So if you also assume isotropy, you basically need the Riemann tensor to be some kind of multiple of Gij. Lots of things have to go away. And so the only kinds of metrics that you can have, right, are going to be the flat Euclidean metric supported on R3, okay, a hyperbolic metric supported on H3, and it should be S3, and a spherical metric or a metric supported on S3. Okay, so the metric also then, right, takes this very specific form. I'd like you to really notice this factor here at the front, which is called the scale factor, and it's going to appear everywhere in what we do. Okay. Now, the way I've written the metric here, okay, I have here spherical symmetry, because this is just d omega squared on S2. Okay, but you also can have metrics that are globally homogeneous and isotropic, but they are not spherically symmetric. Okay, but they need to be supported on manifolds where we take a quotient here. All right, so in particular, the example that's going to be quite relevant here, okay, is that we can also have FLRW metrics supported on quotients of these. Okay, and so in particular, I haven't told you what K is, very naughty. Okay, so K here is the constant sectional curvature of the 3 manifold, right, which up to rescaling can either be positive, negative, or 0. And so if it's 0, of course, you're going to get a metric supported on R3. If it's negative, you'll have something on a hyperbolic space. If it's positive, one will be supported on S3. Okay, but we can also take quotients of these spaces. And so in particular, something that will be quite relevant here is the flat case, right? So that's where the sectional curvature is 0. And your manifold is just T3. Okay, when we take the quotient there. Okay. So a few comments to make about this form, okay, of what we see here with the FLRW metric, okay, is that the cosmological principle allows you to turn the 10 degrees of freedom of a metric in 3+1 dimensions. Okay, it allows us to reduce this degrees of freedom of G mu nu. It allows us to reduce it to just 2 degrees of freedom, okay, DOF, degrees of freedom, which are just this constant K here, measuring the sectional curvature, okay, and this factor A of T here with the scale factor. Okay, so instead of having to solve for 10 things that we don't know, we now only have to solve for 2 things. So that's obviously a big improvement. All right, so what can I say about the scale factor? Okay, it's good to also think, what is this doing? Okay, you can view it as, okay, literally something that scales distance. Okay, a scale factor of distances between fundamental observers. Okay, so e.g., if you've got an observer moving along the line x is equal to x1, okay, and moving along the line x is equal to x2, then they will have a distance, okay, which you can measure using this metric here in the square brackets. Okay, there'll be a distance between these 2 fundamental observers. Okay, and then over time, that distance is just scaled by this factor A of T. Okay. Very good. And another comment to make on this, right, is, and this will become apparent, I'll use this later on, okay, is just to note that we now end up with kind of 2 coordinate systems, okay? We have what's called co-moving coordinates, which I'm going to denote by x1, x2, x3. Okay, so that's these chaps in here. Okay, and we also have physical coordinates, which are those coordinates scaled by scaling factor. Okay, so, I mean, I haven't really told you yet that the universe is expanding, but hopefully you believe it is. And so this scale factor is growing over time, okay? And so you obviously have some kind of intrinsic motion, right? Let's say coming between observers on the grid, but then you've also got the motion of the grid itself expanding, okay? So that's the difference between co-moving, okay, and the physical coordinates. And so in particular, you can change, let me just show you, for example, the physical velocity of, I don't know, a particle, physical velocity, okay, of a particle. All right, so if I were to say, what is physical velocity, right? By definition, it's going to be the change of physical coordinates with respect to time. Okay, we've got some particle moving along this position R here. Okay, and if we just do the chain rule, we see that we're going to get 2 components. The first one coming from A of t times dx of t. Okay, so that's the velocity measured by a co-moving observer. Okay, and then we will have another piece, which is dA dt times x. Okay, and so we can write this as what's called peculiar velocity plus h times r. And I've introduced here something called h, which is going to be very important in these cosmological models. It's called the Hubble parameter. Okay? So just to unpack this a bit more, right, you've got a particle with some velocity. It's moving on some coordinate mesh like here, okay, which is expanding. The particle is going to have its own peculiar velocity, okay, so it's going to, you know, itself be moving, but then it is also moving with the expanding mesh, okay, with this expansion. And so that here is measured by this factor h times r, okay, and so I have a dot, and then I divide it by a and multiply by a, and that's how I turn that into an r, okay, and so this bit here is called the Hubble flow. Okay, so I guess, yeah, the key thing here is, you know, just note these two contributions. And obviously remember that, you know, Earth has its own peculiar velocity as it moves around the sun, and the sun has its own velocity in the Milky Way, in the solar system, and the solar system has its own peculiar velocity in the Milky Way, right? And so we have all these kind of peculiar motions, but we're also then trying to extract out something which is coming kind of more global than that, which is coming from the expansion of the universe, okay, the Hubble flow. Okay, so let me now tell you just a fraction more physics. Again, I realize that a lot of you are your PDE students. You're like, I don't care about physics, but it is good to care sometimes, okay? So the other thing I wanted to say was to do with redshift. Okay, so as you know, if you hear an ambulance that's moving away from you, you hear the Doppler effect, right? You hear a shift in the sound waves, okay, and the frequency that you hear, if it's coming towards you, if it's going away. The same thing happens in cosmology, okay? So you can imagine we've got some galaxy. It is emitting some light, okay? The galaxy itself is moving, right? It might have its own peculiar velocity, so that would redshift its light. But what we're particularly interested in cosmology is the redshift coming from the expansion itself. Okay, so not from this kind of kinematic part, but really how is light redshifted when we observe it. Okay, so let's just say here, redshift in cosmology can come from expansion, okay, of course, and kind of peculiar motion as well. And it's very hard to, you know, work out how to distinguish these two. And so I guess I just wanted to give you the equation that is important here. Okay, so light emitted at some time. So now cosmologists like to label things in the opposite way to how we might think. Okay, so light emitted at some past time t1, okay, will be observed today okay, at time t0 with a redshift given as follows. Okay, so a redshift is the change in the observed and emitted wavelengths and frequencies and all that kind of thing. Okay, so you can write it as follows. So this will probably be emitted over observed. And I'm not going to show you the derivation, but we know that light travels along null geodesics. Okay, it's going to travel on null geodesics of an FLRW metric. Okay, so you can show that actually this rate here is given by AT1 divided by AT0. Okay, so the scale factor at some previous time divided by the scale factor at the present time. And cosmologists just have the habit of using T0 as today. Okay, so if you do a Taylor series okay, of this top scale factor, okay, which only works for small distance. Okay, but I don't really know much about the approximations. I just wanted you to see kind of the next step in this. Okay, so if I do a Taylor series here, and instead of expanding about T1, I'm expanding about T0 with some correction here. Okay, so what is H0? H0 is A dot of T0 divided by A of T0. Okay, the Hubble parameter at time T0. Okay, then things will cancel out, right? And we approximately get here H0 times T0 minus T1. Oh, sorry, Z, because I have a 1 here. Z, okay, is going to be approximately this first linear part here. And we're working in units where C is 1, okay? So T1 minus T0 is nothing but the distance, okay, between just the physical distance between some objects, okay, and the time taken for a signal sent from one of the objects to be sent to the other object, okay, sent at time T1, observed at time T0, okay. So the reason why I kind of wanted to show you this, okay, is just so you see, I mean, you know, you need to obviously, if you want to understand it further, go and understand the derivation, but hopefully you've met, if you've done general relativity before, you've seen that light travels on null geodesics. Okay, you work out null geodesics of the FLRW metric, and you see that that expansion factor A of t, this scale factor, will induce a redshift on frequencies. Okay, and in particular, what this tells us here is it tells us that redshift, okay, should increase linearly with distance. Okay, if we're in an expanding universe, okay, where this number here is strictly positive. Okay, and so this is what was observed. Okay, so in particular, what we see here, okay, on this diagram is we've got here, okay, so here it's velocity, but you could also replace it with redshift. Okay, and here, I mean, this was done in 1929, so it was a very long time ago, right? And Hubble did observations of supernova, okay? And I mean, it's a whole question trying to, you know, work out what all the parameters are, but you notice this incredible linear relationship, okay, between the distance of an object, okay, of something that we might observe, and the redshift of light. Okay, and I mean, it's quite, you know, on Earth, right, we can send photons to each other, so we know frequencies, right? We know lambda, we know wavelengths for certain types of photon emissions. Okay, we know that, you know, lithium has kind of a spectrum that emits at a certain wavelength, and what was observed is a redshift, okay, in that wavelength, and that plots linearly against the distance. Okay, so this is kind of the first observational evidence that was telling us that actually we're living in an expanding universe, which I just want to take a moment to realize, like, that was really quite transformational, right? Because if you think, for thousands of years, right, humans have looked out at the stars and they're pretty fixed, right? Like, you know, we see the horoscopes, like we see these stars, these constellations, we still see them in the same structure as we saw them thousands of years ago. So it looks like everything's static. Okay, it looks like the universe isn't changing. But what this was, and so until this point, it's maybe just worth to mention, before this, it was thought that the universe was static. Okay, and so this is why Einstein came up with his static model, okay, for cosmology, for the universe, and this is why he thought this was a big mistake, okay, but because he realized that actually his static model was expanding, but actually he did the right thing, because it turns out our universe is expanding. Okay, but if you, I mean, a priori, if you just go out and look at the stars, it's not at all obvious that it's expanding, right? You can't see that, right? But we can see it through this redshifting of light, and so since this time, we've realized that this scale factor here, H0, is positive. There's a massive debate happening in cosmology at the moment because they can't agree on the value of H0. And This is called the Hubble tension, which sounds a great name. But it's really quite significant because there are different ways that you can measure the Hubble constant. One of them is to do things like this, okay, is to look at supernova and to look at how light gets redshifted. Another one is to do measurements of the CMB. And at the moment, the numbers H naught, okay, are different. And we're at like 3 sigma and 4 sigma and things like this. Okay, so they're not overlapping. So it's very significant that they're not agreeing. And so a lot of work to be done there. Okay, so I've talked now a lot about the geometry, right? I've talked a lot about the metric, okay, under the cosmological principle. But in Einstein's theory, we know on the right-hand side there should be matter terms. Let me talk a bit now about matter. Okay. So in particular, the kind of the starting point, okay, so from the Einstein equations, Ricci minus 1/2 Rg is equal to matter. If you assume isotropy and homogeneity, or isotropy at every point on the left-hand side, that is going to restrict the kind of tensor you can have on the right-hand side of these equations. Okay, so in particular, okay, the isotropy and the homogeneity is going to restrict kind of all the matter tensor fields, okay, need to also be isotropic and homogeneous. Okay, so in particular, if I have on the right-hand side here, and actually maybe I already just be a little bit more precise. Okay, I'm going to add here cosmological constant, and I'm going to have here on the right-hand side the stress energy tensor T mu nu. Okay, we would like to understand what form can T mu nu take. Okay, if we work in the coordinates, FLRW coordinates that I've just rubbed off, okay, we can decompose this into a 3-scalar, a 3-vector, and a 3-tensor, okay, from the point of view of the spatial sections. So this is going to roughly correspond to our scalar, our vector, okay, and our 2-tensor. If you've got a scalar function that needs to be isotropic in space at every point, it can't depend on space, but it could depend on time. Okay, so in particular, we see that T naught naught could just be a function of time. That's consistent with isotropy and homogeneity. Okay. If you have an index like 0i or j0, right, this is defining a vector. Okay, but just by definition, if you define a vector, right, you're defining a preferred direction. Okay, and we're saying that under isotropy, there are no preferred directions. So the only way for this to be compatible, right, with what we want is actually that these parts here should vanish. Okay, T naught I and Tj0 should be 0. And lastly, the only isotropic 2-tensor in 3 dimensions is just going to be proportional to delta. Okay, so if you kind of work kind of near a point, you see that the only option for this tensor, the remaining part of this tensor Tij, the only option it has is to be proportional to. Okay, so that's what this symbol means here, just because I'm going to use this a bit. Okay, and if you work in normal coordinates, right, this is just going to be proportional to your metric, Gij m, I think is what I was calling it. Okay, and what can we say about the factor that comes in this proportionality? Okay, it can just, again, because kind of how I argued here, it can just be a function of time. It can't also depend on space. Okay, so in particular, we get that Tij must be some function of time, okay, time symmetric, Gij. So I have called these rho and P because these are actually going to map to the energy density of a perfect fluid, okay, and the pressure of a perfect fluid. So I can also write this covariantly, okay. Okay, and I'll put the index up and down, not that it really matters. Okay, we see that if you've got all these restrictions on the left-hand side of the Einstein equations, okay, the right-hand side, the matter tensor needs to take, stress energy tensor needs to take this form, okay, where this rho is just a function of T and this P is just a function of T, okay. And it turns out that this is the stress energy tensor for a perfect fluid in relativistic, in general relativity. Okay. So let me just say here, what is U? Okay, so what I've written here. Okay, so this is just the relative force velocity, okay, between the fluid and an observer, okay, and so this velocity vector is just going to be 1, 0, 0, 0, okay, for a co-moving observer. Okay, so a fluid that's just expanding with the expanding geometry itself. Okay, so I guess I have to kind of hope that you'll accept, I mean, I know I've been telling you lots of things you've just got to accept, okay, is just to believe that this is the stress energy tensor of an idealized fluid, okay, which we call a perfect fluid. So we have fluid mechanics in Newtonian, like we just have fluid mechanics, right? And then you might want to put in gravity. You start with Newtonian gravity. And then you might want to promote that to relativistic theories. It's not at all well defined how to do this in full generality. Okay, so you think fluids have entropy and viscosity. Okay, but in order to map that to the relativistic world, there is actually no canonical way to do that. But things are on a lot more steady footing if you suppose that your fluid is highly idealized, which means that it's just described by its energy density and its pressure. Okay, so we suppose that entropy is constant. We're not worrying about other thermodynamic variables. Okay, and in, for reasons that beyond me, in cosmology, this is actually all they're interested in. Okay, they're not worried about these. That comes later in their models. Okay, so we have restricted the matter. If we think, what are we doing? We're trying to solve the Einstein equations in cosmology. We've got restrictions on the left-hand side telling us that the metric should be FLRW. On the right-hand side now, we see here that the matter should be a perfect fluid. Okay, so we can now start to derive some equations of motion. Okay, so not just using symmetry, but also solving these equations here. So the first equation that I want to talk about is the continuity equation. Okay, so from the conservation of local stress energy, okay, on the left-hand side of the Einstein equations, we get this conservation law here on the right-hand side for the matter. Okay, now this equation here, okay, if we're looking in this highly symmetric case here for nu, right, if you take nu to be a spatial index, the equation is automatically satisfied because we just don't have any off-diagonal components here. But when nu is equal to 0, okay, then I need to expand out something like this. Okay, yeah, you can write indices up and down, however you want to do that. And in the interest of time, I'm just going to tell you what you get. I'm sorry. Okay, well, maybe it's actually good just to say one word about this. Okay, because we need to expand out the mu index. Okay, so we're going to have something like this. Okay, and then we're going to get two Christoffel terms, okay, that come from when the covariant derivative acts on the first index and the second index. Okay. So I'm not giving you the indices because it's just a little bit of computation to work that out, but it so happens that, actually maybe I can even just write down, the only non-zero ones are as follows. Well, the only non-zero parts that we get here come from these particular Christoffel symbols. I probably should have written a T there and a 0 there, okay, because the T naught I component is 0, okay, and so altogether we end up with the following equation as follows, right? And so this is the continuity equation, which here we've derived from Einstein's equations, but you can also derive from local conservation of energy density. Okay. And so what to say in cosmology, okay, maybe something to, again, a little bit more cosmology here. Our best understanding at the moment is that our universe is made up of different matter components, which in certain scenarios can be described by this idealized perfect fluid. Okay. So maybe just stay here. Okay, so the universe is made of different, say here, fluid matter components. And there's three kind of very important matter components that are used. Okay, so the first matter component is what's called dust. Okay, and so this is when the pressure is much smaller than the energy density. Okay, and what is typically done is we just assume that the pressure vanishes. Okay, so as an example here, this is what cosmologists use to describe baryons. Okay, so this is the kind of nuclei and electrons. So the particles are kind of baryons, a fluid of baryons. It's also used on other scales to describe galaxies, okay, because they're so big, they're just interacting through the gravitational force, okay, at kind of the large scale that we might want to model them at. Obviously, at a local scale, you need to do something a lot more complicated. And there's another component, right, which is called cold dark matter. Okay, so dark here is the fact that we can't see it. Okay, that's what that means. It's matter because we believe it's pressureless. Okay, and I guess it's cold also because it's not a relativistic kind of matter source. And we don't know what this is, and this is one of the big issues in cosmology, is that just again, this intuition, things are expanding, right? Gravity is attractive. If you have more mass, you have more gravitational attraction, so you might expect you're more likely then to form a structure. Okay, and cosmologists, there are certain kind of galaxies out there that they don't know how to model unless there is some additional matter component which is pulling the galaxy in and giving it its structure. Okay, so that missing matter component is called cold dark matter. Okay, and it's just like a black box that cosmologists put in their models. okay, which is obviously very unsatisfying, but just so you know the state of cosmology. And then there's another type of matter, fluid matter, that we'd like to include. And this is that of radiation. Okay, and in this case, it turns out that the pressure takes the form of 1/3 times the energy density rho. You might say, why on earth is it 1/3? Okay, this is because if you look at the trace of the Maxwell tensor, stress energy tensor is 0. Okay, so you would think that if we're going to model some kind of relativistic gas of, like say photons, okay, some collection of photons, you would hope that the stress energy tensor of the photons modeled as a fluid, that trace should also vanish. Okay, and so for that trace to vanish here, you need to set P to be 1/3 of rho because we're in 3+1 dimensions. Okay, so it's just coming from that fact. Okay, so I'll also mention finally, there is another component called dark energy. Okay, and then this is when the pressure is actually negative. Okay, so you think you've got some energy density, some clump of matter, the pressure is negative, so somehow it's pushing everything away. Okay, and this is another way that you can take the cosmological constant on the left-hand side of these equations and you can put it on the right-hand side of the equations. Okay, so let me just kind of make that. It's a very small aside, but it's just a small comment. Okay, so from kind of what I'm quite interested in, okay, is going to be this case here, 1 and 2. Okay, and I will, I guess more generally, I'm going to be considering, and this is what is done in cosmology, is some equation of state that is just a linear, okay, sorry, I didn't say that a bit too fast. So we have a fluid, and we have here an equation for rho in the continuity equation, but the other equation here, nu is equal to I, doesn't tell us any information. So we don't have enough equations to solve because we also need to solve for P. Okay, so we need to have a relationship between P and rho. So the first case is just what I said here, P is 0. Second case is P is 1/3 rho. Okay, and kind of in cosmology, they package this all together and they say, in general, we can have P is equal to K times rho. So I should end. So let me just end with very quickly putting these different matter components into the continuity equation, right? Because once we know how the pressure P here relates to the energy density rho, you can integrate this up. Okay. So in particular, if you substitute into the continuity equation here, okay, you will get that the energy density rho goes like a to the minus 3, okay, which is just to say, like quite literally, rho is equal to some constant over a cubed. In the case of radiation, okay, we see that the energy density scales like 1 over a to the 4. And actually here you see that it actually scales like a constant. But that case is not so important. But in general, actually, let me write down the general case down here. Okay, we see that the energy density here scales like a to the minus 3, 1 plus k. So why is this important? It's important because you should imagine that when the CMB was admitted, okay, we had some small density of baryons, okay, particles that were starting to form. And then we had lots of radiation, okay, the CMB radiation itself. And we had cold dark matter, which we don't really know what's going on there. And how do their densities evolve as time increases? Well, certainly they're going to dilute, right, because you can't create matter from nothing in these classical models. The universe is expanding, so you expect dilution, but it's very important to understand the rate of that dilution. Okay, so we see here that actually the radiation dilutes faster, okay, whereas the cold dark matter does not. Okay, and that's kind of going to be very important, just that kind of level to understand what we do tomorrow. But I think that's a good place to stop. Okay, and then I will carry on tomorrow. Very good. And we will meet a PD tomorrow, I promise.